created by MindSticks Foundation Trust.
Welcome, students. Today in this explainer, we are going to explore the hidden and fascinating behaviors of water. We will look at latent heat, regolation, water's anomalous behavior, Hope's apparatus, and finally, dew point and humidity. Let us move forward at a comfortable, steady pace so we grasp every concept clearly. All right, let us dive right into our first topic. We will begin by observing what happens when ice melts and water boils. More importantly, we need to ask ourselves, where does the heat energy actually go during these changes? This brings us to the concept of specific latent heat. Now, when ice melts at 0 degrees Celsius, it is constantly absorbing heat from the burner, right? But the temperature does not rise at all. You might be wondering, where exactly is that heat going? Well, the heat is busy. It is working to weaken the bonds between the molecules in the solid state. It is hidden energy, and that is exactly what the word latent means. Look carefully at the graph on your screen. Do you notice that flat horizontal line from A to B? Here, the ice is turning into water, but it is keeping a perfectly constant temperature of 0 degrees. Then, look higher up at the line from C to D. Here, the liquid water is boiling and converting into steam, again maintaining a perfectly constant temperature of 100 degrees. The heat supplied during these flat phases is the latent heat of fusion and vaporization. Now, the crucial takeaway here is that different materials require vastly different amounts of this hidden energy. If we compare water to heavy metals like copper or gold, we can clearly see that water demands an enormous amount of latent heat. Just look at the vaporization column. It takes a massive 2,256 kilojoules per kilogram just to turn water into vapor. This exceptionally high requirement is a very special, defining property of water. Moving on, let us talk about something I like to call the ice trick. Can you recall seeing ice golas being prepared by street vendors? They shred solid ice, press it around a stick, and suddenly it becomes a solid ball again. Let us understand the science behind making ice stick together like that. Imagine setting up an experiment just like this. You place a thin metal wire with heavy weights hanging from both ends, right over a solid block of ice. If you do this, something almost magical happens. Over time, the wire will actually pass right through the ice block, but the block itself will not be cut in half. It remains completely intact. Let us break down the exact steps of what is actually occurring here. First, the applied pressure from those heavy weights forces the melting point of the ice directly beneath the wire to drop below 0 degrees Celsius. Because of this, the ice melts into water without any added heat. Second, the wire naturally slips down through that tiny layer of liquid. But here is the third crucial step. The moment the wire passes, the pressure above it is gone. The melting point instantly jumps back up to 0, and the water immediately freezes again above the wire. This amazing phenomenon, melting under pressure and instantly refreezing, is what we call regelation. Now, let us move to a truly life-saving quirk of nature. We are going to look at the anomalous behavior of water. You see, water behaves very, very differently from almost all other liquids when it gets cooled down. Generally speaking, liquids shrink and become denser as they cool. But water? Water has a very special exception. If we cool water down from room temperature, it contracts normally until it hits exactly 4 degrees Celsius. At this exact point, it achieves its maximum density. But if we cool it even further, dropping from 4 degrees down to 0 degrees, it does not shrink. It actually expands. Its volume increases. This unusual expansion is what scientists call the anomalous behavior of water. To prove and carefully study this special behavior in a laboratory setting, scientists use a brilliant device designed precisely for this purpose, known as Hope's apparatus. Take a close look at how it works. Observe the freezing mixture of ice and salt placed in that flat bowl around the middle of the cylinder. As the water in the middle cools towards 4 degrees, it becomes denser and heavier, so it naturally sinks to the bottom. Because of this, the lower thermometer drops rapidly to 4 degrees. Meanwhile, the water that cools below 4 degrees actually expands, becomes lighter, and rises to the top. This causes the upper thermometer to eventually drop all the way to 0 degrees first. Now, why does this matter? Well, this anomalous behavior is absolutely crucial in the real world. It is the exact reason why an ice layer forms only on the surface of lakes and ponds during freezing winters. The ice stays on top because it is less dense, and it acts like a protective, insulating blanket. This preserves the warmer, denser 4-degree water down below, which allows fish and other aquatic life to survive comfortably through the harshest winter months. Nature has a truly profound way of protecting life, doesn't it? Finally, let us look at the invisible water that is constantly surrounding us in the atmosphere. Let's talk about dew point and humidity. You know, warm air has the capacity to hold a very large amount of water vapor. But there is a strict limit. If we take unsaturated air and start to cool it down, its capacity to hold moisture steadily decreases. Eventually, it reaches a specific temperature where it can hold absolutely no more vapor. It becomes fully saturated. Any further cooling will force that excess vapor to condense into tiny water droplets. This exact temperature boundary is what we call the dew point temperature. Now, let us clarify how we actually measure this atmospheric moisture. Absolute humidity is simply the sheer weight, the actual mass of vapor present in a unit volume of air, usually measured in kilograms per cubic meter. However, when you hear weather reporters on the news talking about moisture, they're almost always using relative humidity. This is a ratio expressed as a percentage. It simply compares the actual moisture present right now to the maximum amount the air could possibly hold at that specific temperature. As we conclude this explainer, I want to leave you with a question to really test your understanding. In cold regions during the harsh winter, metal pipes used for water supply often burst open, and even solid rocks can crack. If you remember what we just discussed, that water uniquely expands and increases in volume when it cools from 4 degrees to 0 degrees and freezes into ice, what do you think happens to those rigid, restricted pipes holding that water? Keep wondering about these everyday phenomena. Apply what you have learned today and keep learning. Thank you for joining me.